You might have heard of this thing. It's a pretty big deal. It's called AI. There's a bunch of different models now that are capable of a bunch of very exciting, very useful, and sometimes vaguely dystopian things. So what's the deal, right? Like, why is there so much AI that's so good at so much stuff? Well, what I think is really interesting is it's all derivative from the same fundamental architecture. There's this one architecture that was released a few years ago that really triggered this modern Cambrian explosion of the modern AI wave. And in this video, we're going to be talking about that architecture. My name is Daniel Warfield, and this is the Transformer, intuitively and exhaustively explained. Now, before we actually dive into the Transformer, I want to take a brief moment to describe some of the artificial intelligence that was happening before the Transformer was created, so we can understand the world it was envisioned in, and some of the things that it does differently than previous AI approaches. Our story starts with natural language processing, which is a fundamental idea in artificial intelligence that basically concerns a branch of models that are designed to do something with natural human text. So for instance, if you get like a review on your website and you want to know which reviews are positive and which ones are negative, maybe you want to generate text. So receive some text from a person and then generate some response. These all fall under the purview of natural language processing. Now, one really interesting and subtle idea in natural language processing you might not have noticed: words are not numbers. And artificial intelligence relies on models that manipulate numbers. So somehow we have to turn our words into numbers. And a fundamental idea in this is what's called the word embedding. The idea of a word embedding is to find clever vectors that you can associate with every word. So I like to think of this as like an organization problem. You have all these words that have meaning, right? Like the word dog and dogs has some relationship. The word king and queen have some relationship. The word man and woman have some relationship. These words have some relationship with each other that carry some implicit meaning. They're not random. So the idea of a word to vector embedding is to encode this information spatially. So essentially what you do is you build a very clever model that looks at a bunch of words in the English language and tries to organize them such that they obey some rules. One of my favorites is word2vect, which had a very daring idea to be able to do algebra with words. So like, what if we could organize all of our words such that, for instance, if you took the vector for king, subtracted man, added the vector for woman, you might get the vector queen. That kind of makes sense, right? If you take away masculinity and then add femininity to the vector king, then you would end up with queen. Word to vector embeddings have to some extent fallen out of favor in favor of just lookup tables. So we won't get into the weeds too much, but it's important to note that when the transformer was invented, this is a very, very popular paradigm, and it's something that the transformer originally heavily relied on. That's really cool. The important part for us, though, is that now all of our words are vectors. So all of our words represent numbers now. So now we can build models on top of them. And a very popular approach was something called the recurrent neural network. Now, you might understand or have some sort of association with the traditional neural network. This is basically a collection of neurons that when you input some information, things get multiplied by certain weights, added together, and then also passed through something called an activation function in order to result in another layer of neurons that can then get passed through another layer of neurons, et cetera, et cetera, et cetera, kind of down the chain. And this is a lot of people's sort of fundamental understanding of AI, is you have this sort of neural network. The recurrent neural network is fascinating because you essentially take that idea and you turn it into a cycle. So instead of passing data through a neural network, you have a neural network feed back into itself, and this is called recurrence. This is a really popular approach in natural language processing because in natural language processing, you can get very long sequences of text, and you need to be able to process all of those sequences of text without maybe even knowing how long that sequence of text will be. So long story short, recurrent neural networks are super cool, and they dominated natural language processing for a very long time. They were very good at a process called translation, which you probably know about. It's turning a sequence of words in one language into a sequence of words in another language. Now, you might think translation is a trivially easy problem, but it's actually very difficult. For instance, if you take even the simple phrase, I am a manager, and you try to translate that into French, you would get je suis directeur, which is you're turning 4 words into 3 words. And the word suis is a conjugation of the verb être, which is to be, and that's conjugated by the fact that it's I rather than you, he, she, or they. So you actually need to know a lot about the implicit grammar. You also sometimes need to know about culture when translating. There's some things that don't translate well and you have to find a better translation. There's actually a lot you have to know to be a good translator when you're translating from one language to another. So the naive approach of just turning a word into a word in the different language usually doesn't work. The way data scientists dealt with this was with a process called sequence to vector to sequence modeling. Basically, the idea was instead of trying to translate every word, what they would try to do is they would try to embed the input. And what that means is you feed the input through a model. So I am a manager, you feed that through a model, and you get the model to create a numerical representation that's designed to represent the entire input. And this is an abstract, big hunk of numbers that the model kind of learns throughout the process of training. But essentially what it tries to do is it tries to distill the entire input sequence into a big hunk of numbers. And then you create a decoder that then looks at that big hunk of numbers and then decodes it into a different language. And what that allows you to do is to distill an entire sentence so that the model can account for that entire sentence when it's doing the translation. The idea of sequence to vector to sequence modeling in terms of translation was super powerful in the translation arena and opened the door for all sorts of compelling and very effective translation models. But there was one kind of big problem, which is that if you're translating a long sequence, right, a very long sequence, a very, very, very long sequence, you have to squish that entire sequence down into this embedded space. And this is kind of problematic because the more information you try to squeeze, the more likely you are to lose some information. There's only so information you can squeeze into this finite vector that lives between both of these sequences. The way data scientists got around this was with a very clever strategy called attention. I like to call this as attention through alignment. It was a popular approach in the sequence to vector to sequence modeling space. Basically what you would do is when you pass your data through your recurrent neural network to generate your encoding, you have all these intermediary representations within the recurrent neural network itself. And what you do is you build what's called an alignment model, or what I like to call an alignment model. And what that model does is it goes, which words do I think is actually relevant right now in this part of the translation? So instead of encoding the entire input into a vector, you turn the vector into a series of smaller encodings that are relevant to the particular word you're currently trying to translate. And this is incredibly compelling because it allows you to kind of have your cake and eat it too. You can distill things, but you can also ignore things that aren't really relevant when you're doing a particular word's translation. Super freaking cool. So everything was grand. The recurrent neural network had its throne atop the natural language processing pyre until the transformer totally kicked the door down and flipped the script on all of natural language processing forever. And this is the transformer. This is what we're going to be discussing for the rest of the video. Now, this might look incredibly daunting, but it's actually not as complicated as you might think, and it certainly isn't as complicated as you might expect for revolutionizing all of technology as we know it. So it's actually relatively straightforward. Off the dome, you might notice some vague similarity. There's this thing called an encoder and a decoder, and it's actually very similar to the recurrent neural network. You have something that is designed to take in some input sequence, and then another thing that's designed to take in the sort of embedding of that input sequence to generate an output sequence. If we take a brief look within the transformer, you might notice a word that we've mentioned before called attention. Now, this is a different mechanism than the one that we discussed previously. We'll discuss this one in depth, but it has the same core idea. How should we sort of relate this information with that information? Now, I know that's very vague. We're going to get into some more specifics, but attention, this idea of figuring out what is relevant to what other information, is a fundamental component of the transformer. Actually, it's so fundamental, the paper that introduced the transformer was called Attention is All You Need. recall with the recurrent neural network, we were kind of feeding data into the model sequentially. So you have the phrase, I am a director, you add the word I, then you add the word am, and then you add the word a, and you add the word a director. So through it kind of existing the way it does, a recurrent neural network learns an implicit structure. It learns about sequences. It learns what it means for a word to follow another word. The transformer, it doesn't actually have an implicit understanding of order. So when you pass in a phrase, I am a director, into the input of a transformer, it kind of doesn't know what order you pass the words in. And we'll get into exactly why that is later from a conceptual perspective. But one of the first things that you do is you do what's called a positional encoding. So all of our words, I am a director, we might embed them with word to vect. So we represent each of them as a vector. And that's a completely separate model that we've sort of co-opted to turn our words into vectors. So it's convenient for us to build models off of. And then what we have to do is we have to add positional information. They essentially add squiggly lines to every word. And the lines get more squiggly throughout the input. And what that allows the model to do is be able to look at two vectors and see which one has more squiggly lines. If this one has more squiggly lines, then it's later in the sequence. Now, this is really important. Our vectors themselves contain information about the word and also information about where that word is located. Once our input sequence has been properly treated, so we've turned it into a vector and then we added positional information to it, we then pass it through a section of the model called the encoder. And the encoder's job is to take our sequence of vectors and turn them into a dense, abstract, and meaning-rich representation that the decoder can use to construct the output. If we dive into the encoder to try to explore how it's creating this meaning-rich representation, there's really three components. There's the multi-headed self-attention, here called multi-headed attention, but in the business we call it multi-headed self-attention. There's also add and norm, which we'll discuss, and there's a feed forward, which we'll also discuss. The most important part, and probably the most revolutionary idea in the transformer, is multi-headed self-attention. Basically, the idea is, instead of trying to figure out how an input should attend to an output, like in the recurrent neural network example we discussed previously, self-attention tries to say, which inputs should we relate with each other? Which inputs should have their information interact with each other so that we can create a abstract representation that includes the interaction of all of the input tokens, or all the input words rather, with all the other input words. This is maybe a little weird to think about abstractly, so let's try to dig into multi-headed self-attention and kind of get an idea of how it makes these abstract representations. Multi-headed self-attention starts with something that you might be familiar with, a classic neural network. You just have a bog standard basic neural network that turns our input into some output. So we pass in, I am a director. We've turned all of those words into vectors and we added positional information. So now we have a vector for each of those words. What we do is we feed each of those vectors through the same neural network, and that neural network turns that list of vectors into a new list of vectors that's different. Now, this is kind of an important idea in AI. When you create an AI model, it's initially completely random, right? So you create some stupid representation of your input, but you end up training it to be better at stuff. So anytime you see a neural network do some sort of operation, think this operation will start getting better for the task of generating a translation through the process of training the model. So just kind of keep that in mind. But we take our sequence of words and we pass them through a neural network to create basically a new sequence of vectors that is sort of a transformation of that original sequence of vectors. And we do that 3 times. We pass our input through 3 different neural networks that generate 3 different representations, and we call these the query, the key, and the value. They're vaguely based on databases, but they don't really, the names don't really honestly matter at all. What matters is how these different representations of the input interact with each other to create a new output. Once we've constructed the query key and value, these then get subdivided into what we call heads. Now, this is somewhat of an arbitrary step. It's just super useful from like a practical modeling perspective. It doesn't really impact the theory very much. So for now, let's just consider one multi-headed self-attention head. So assuming we have one multi-headed self-attention head, so we took our sequence of vectors and we pass them through a neural network to create the query key and value. What we do is we take the query and we take the key and we use them to do an interesting operation. So we take the key and we rotate it by 90 degrees. We call that a transposition. And then we do a process called matrix multiplication, where we multiply the values in a row of the query with the values in the column of a key, and then we add the results together to result in one value. So all the values in every row multiply with all the values in every column, and then are added together to create basically this row's interaction with this column. Now it's really useful to kind of think about what this means, right? We took the key and we rotated it on its side. So now the rows of the query represent every word. The columns of the key represent every word. And now we're getting every word to interact with every other word to generate a number. So we've constructed this new matrix that includes every word, or a representation of every word in the input, interacting with a different representation of every word in the input. So all of our words are interacting with all of our other words to create this matrix of numbers. The next thing we do is we apply what's called row-wise softmaxing. So we take on a particular row, we take all of the values and we make them exponents of e. So we do e to the whatever value a particular element in the row was. We also add up all those values, and then we divide exponentially raised values by the sum of all of those values. Sorry, that was a horrible explanation, but I mean, it's cool. You're raising e to the whatever, so it's nonlinear. If you're like a data science nerd, that's important. But what's really conceptually important here is what's fundamentally happening. So we're taking the percentage kind of all of the values that a particular element in this row is. So these are mutually exclusive. If you have a really big value, all the other values become close to zero. If you have a bunch of values that have about the same size, then all of the values in this row end up being about the same size. So you kind of have to choose, right? Do you want all of these values to be similar, or do you want some values to be really high and some values to be really low? And that's kind of the end result of the softmaxing operation. Now, why did we do this row-wise softmaxing? Well, we did it to turn what we previously called the Z matrix, which was the multiplication of the query and key, into the attention matrix. So after we've done the softmaxing operation, we call that the attention matrix. That should give you a hint that there's something very special about the values in this matrix. See, what we do is we multiply this by the value matrix. So recall at the very beginning of the multi-headed self-attention explanation, we turned our input sequence into three representations: the query, key, and value. We just used the query and key to construct the attention matrix. Now what we're going to do is we're going to multiply the attention matrix by the value matrix using matrix multiplication. Now, it's subtle what's kind of going on here, but when you understand what's going on, it really unlocks a lot of the beautiful intuition of the transformer. So when you multiply the attention matrix by the value matrix, you multiply all the rows by all of the columns, and then you add them together to create a single result. And then you move to, let's say, the next column in the value matrix to calculate a new result. The next column in the value matrix to create a new result. And you do that for a single row in the attention matrix, and then you move down a row in the attention matrix. So what you're doing here is every row is, you can think of it as a percentage. You're multiplying these rows by these columns and essentially saying, what percentage of every word becomes a new word? So the attention matrix is saying, how much am I combining these values together? How much am I taking this word and squashing them together? Am I taking these 3 words and squashing them together? Am I just taking this word and squashing them together? Am I taking all of the words and squashing them together? By multiplying in this way, you're allowing the model to look at the input, say, what should I correlate together based on the input itself in generating the attention matrix? And then you're using that to actually do the correlation by multiplying it by the value matrix to create the result of multi-headed self-attention. I'll let that sit because it's absolutely bonkers. This is really the fundamental thing that allows the model to think about the input so that it can create that dense, meaning-rich representation that the decoder uses to construct an output. Now, before we move on to the rest of the transformer, I promised that I would discuss multi-headed self-attention, and it's really just a very slight manipulation of this general strategy we just discussed. So we took our input and we turned it into a query key and value using neural networks. What we can do is we can take those query key and values and we can slice them up. So you might slice them up 2 times, 3 times, 8 times, 10 times. And it doesn't really matter. Well, it does matter if you're like building a model, but the essential idea is you're choosing how many different ways the model can do multi-headed self-attention. So let's say we use 2 heads. What we're going to do is we take the first partition of the query, the first partition of the key, the first partition of the value, and we pass each of those to multi-headed self-attention head 1. Then we take the second partition of all of those and pass them to the second head. So if we look into the first head, we do all of the same things that we previously discussed. We take the key, we transpose it, we multiply that by the query. That results in the Z matrix. We then do row-wise softmaxing to then generate the attention matrix. We multiply the attention matrix by the value matrix to result in the output of that head. If we look at the second multi-headed self-attention head, we take the query, we multiply it by the transposed key to create the Z matrix. We do row-wise softmaxing to generate the attention head, the attention matrix, and then we multiply that matrix by the value matrix to result in the output of multi-headed self-attention head 2. Then what we do is we take each of those outputs and we just stick them back together. So it's the same size output as if we just did one big multi-headed self-attention, but we've allowed the model to do it in parallel in 2 different ways. Now, this is really compelling because it allows the model to reason about the same input in multiple ways, which can be, well, the research has shown is incredibly beneficial, which is why it's such a common strategy. Oh my gosh, look at the time. Are we ever going to get through this? Yes, because actually we just covered easily the most complex topic in the transformer, and we actually just do a few other relatively simple operations and then just combine them together a bunch of times. So let's keep going through the encoder. Recall the encoder's job is to take our input phrase, I am a director, and then turn it into a meaning-rich representation. So after multi-headed self-attention, we have what's called a skip connection. Here it's shown as add. This is useful for training. When you're training a model, there's something called a gradient, and things can get very confusing for the model if you have a bunch of operations that kind of add on top of each other. So it's useful to take a older, simpler representation of the input and kind of add it onto our more complex representation that we got through multi-headed self-attention. So what we do is we take the output of multi-headed self-attention and whatever we had as the input, which here is just like the sequence of words, and we add them together. So it's kind of a balance between this super contextualized, vague, abstract representation and the kind of easier to understand representation that we had previously. That's useful for training the model. Now that we've done all of this crazy math, we have a bunch of crazy numbers. We might have really big numbers, we might have very small numbers. Neural networks are famously really bad at dealing with vastly differently sized numbers. It can kind of explode the training process. So what we do is what's called layer normalization. So after we've done multi-headed self-attention and then added our previous representation, we look at all the values and we squash them down into a reasonable distribution. So they have the same general structure, but all the big numbers have been squashed down to something reasonable. All the small numbers have been brought up to something reasonable. and now it's within a reasonable distribution. There's one more operation in the encoder which we haven't discussed, which is a neural network. We have a dense network, is what's, I believe, listed in the diagram. A dense network is just a neural network. So neural networks take in a vector and then they output a vector. So what we do is we have a neural network that looks at all of the vectors in our now modified sequence and then just turns them into an output. That is, vectors that mean slightly different things, but in the same general shape. So actually, this is essentially exactly what we did in the query to generate the query key and value within the attention mechanism. It's just now we're using it to actually generate the values within the model rather than to generate like intermediary values. You can kind of think of this as just another way the model can learn to manipulate the input to create a good representation that it can then pass to the decoder. All of these elements that we've previously discussed, the multi-headed self-attention, add norm, feed forward, these all exist within an encoder block. So it's really useful to note all of these operations, they don't change the shape of the input. So if you have some sequence of words that's some length and each of those words is represented with a vector that's, also some length, the output will have the same shape as your input. Now this is really useful because that means you can actually pass these values to another encoder block. So you can, take your inputs, pass them through an encoder. You do this abstract representation, so you get all the words to interact with each other. Now you have a new list of representations for your words that you can then pass to another encoder block, which will, based on that representation, create a new representation. And you can pass that through another encoder block, which can create a new representation. You can imagine by kind of daisy chaining these complex operations together, you could get a model that could really do some serious introspection about the input. It really can make incredibly abstract, human incomparably abstract representations of the input that can contain some very dense and meaning-rich information. And then we can use that and feed it into the decoder to construct the output. So we've basically covered the entire encoder, and we have a pretty good idea of how it functions. The decoder, it might look a little different, but it's actually, to a large extent, virtually the same. We have a input embedding, so we take all of our input words and we embed them. We add positional encoding. We do something called masked multi-headed self-attention, which we'll get into, but it's a flavor of multi-headed self-attention. We have add norm. We have another attention, but here it's not called attention, it's called cross attention. We'll talk about that. We have another add norm. We have feed forward, and then we have another add norm. So really, it's virtually the same, the decoder block, except instead of multi-headed self-attention, it's masked multi-headed self-attention. And we've also injected this other attention, which we're calling cross attention. So before we dive into these differences, I want to take a second to really talk about what the decoder actually does, what it does during training and what it does when it's actually generating stuff, right? So imagine we have our input phrase, I am a director, and we want to translate it to je suis directeur. Assuming we had a model that was actually trained, the way this would work is we would feed in the phrase, I am a director, to the encoder. Then we would feed in a word, a special word. It's actually not a word at all. It's called a token, the start token, to the decoder. So this is essentially a special word in our vocabulary that has its own vector associated with it. And this tells the model, hey, we're starting a sequence now. So we give it the start sequence followed by a bunch of pad tokens. So these pad tokens mean we don't have any information here yet. There's no information. So what we do is we take, our input phrase, I am a director, and the start token followed by this bunch of pads, and then we try to get the decoder to predict the next word in the sequence. So je, because the next word is really the first word after we say, hey, we want to start outputting stuff. So the next word is je. Then what we do when we're inferencing with our model is we take the word je and we move it back into the input. So now we still have the same encoder input, which is I am a director, but now the decoder input is start je. So when we pass start je into the decoder, what we want the decoder to do is generate the next word, which would be suis. And then we have the same input again in the encoder, but now we take suis and we move it to the input of the decoder. So now we have start je suis, and then we want the decoder to output directeur, and then we do the same operation again, and then we want the decoder to output a new special token called end. So this process of generating words or tokens one at a time is called autoregressive generation. Every time you create a new thing, you're sticking it back into the input so that you can generate another new thing. Now, this is very similar to the recurrent neural network, right? The recurrent neural network, you generate a thing and then you use the results from the previous generation to generate the next thing, so on and so forth. But I'd like to remind you what the encoder block did, right? The encoder block, it took a sequence of vectors and it turned them into a different sequence of vectors. What the decoder block does is it does the same exact thing. All of our inputs that we're adding into the decoder get turned into new vectors. So we're not just outputting one word vector, we're actually outputting many word vectors. So what are these word vectors? They're actually not just the next word in the input sequence. They're all of the next words in the input sequence, as if future words didn't exist. So this is a really weird but incredibly important idea in the transformer. So what we do is we feed in a sequence. Let's say we take the entire desired output. So we input into the encoder, I am a director, and we input the entire desired output into the input of the decoder, which is start, je suis directeur, and then a bunch of pads. What we end up getting, or what we want to get in the output, is not just, the next token. It would be all of the next tokens for every spot. So start would turn into je would turn into suis would turn into directeur would turn into end, and then end would turn into pad, and then all the other tokens would turn into pad tokens. So this is a really interesting concept, because now imagine like we have a bad model that we just built and we're trying to train it, right? What we do is we feed it what we want, which is I'm a director and je suis directeur with start and end and pad tokens. And then it outputs some garbage. It might say some other random sequence of French words that doesn't even make any sense. And what we do is we update the model based on every next word prediction, not just one at a time. We give it the entire output that we want, and then we get every prediction at every step of the output. Then we update the model based on that output. And that's a fundamentally different idea than recurrent neural networks, and actually why the transformer is so much more effective than recurrent neural networks. Because recurrent neural networks, you had to feed everything one at a time for every single sequence. If you wanted to train on a book, it would take forever, because you have to feed it every single word one at a time. With transformers, you can feed massive amounts of text into the input, into the output, and you'll get back a response with one pass of the model, which is absolutely bonkers. Now, let's kind of take a more conceptual perspective of this. Imagine I gave this job to you, right? I said, hey, here's a list of the sequence of words that I want. Find all of the next words. So for the first word, give me the next word. For the word after that, give me the next word, etc., etc. This would be a really easy problem, because what you would do is you would just copy the next word. You would just shift the entire sequence over by one, right? Easy peasy. And if we just kind of had a naive neural network, that's exactly what the neural network would do. It would look into the future. For the start token, it would say, hey, what is the next token? Oh, it's je, that's what I should output. So it would be a trivial problem, and then the model wouldn't really learn much, right? If you tried to train a model to find the next word and you gave it the next word, then it would just learn to copy it. That's why we use a process called masking. Now, recall that the attention mechanism, allows every word to interact with every other word. And that's how the words interact together within a transformer. The neural networks operate on a per vector basis. They don't allow them to crosstalk between each other. So it's really the attention mechanism that allows vectors to interact with one another. And recall that it's essentially like a weighted average, right? So the rows in the attention mechanism say this word should interact with that word. What if we added rules to our attention matrix? What if we said certain words couldn't interact with one another? For instance, what if we said that a particular vector in the input of the decoder couldn't see and it couldn't interact with any future words? If we said that throughout the entire decoder, all of the blocks stacked on top of each other, if we said this vector could never see any other vector, and then we had the sort of end result of that vector form a prediction of what the next word should be, what we're doing is we're hiding future information from that vector and then asking that vector to predict the next word. This is really important because it allows the model to actually make a genuine prediction for every future word. At this vector, it cannot see the next vector. At this vector, it cannot see the next vector. So when we generate a prediction, it genuinely is a prediction of all of the next words in the sequence. And that's fabulous and fascinating because that means we can train a model on a bunch of predictions simultaneously. The way masking actually happens is by adding cleverly placed negative infinities, and the way the math shakes out is when you add those negative infinities to the Z matrix and then you do row-wise softmaxing, it ends up as zeros in certain locations, and if you place those locations right, you end up making every vector only be able to attend with itself and every previous vector. The cross-attention mechanism. This is the really last topic we have to discuss to really form a pretty solid understanding of the transformer. And it's actually pretty straightforward. Recall that in multi-headed self-attention, we generated the query key and value based on a single input, and then used those values to kind of correlate that input with itself. In cross-attention, we do something similar, except we take in two inputs. Here, we're taking whatever value exists within the decoder, and we're using that to generate the query. And then we're taking whatever the encoding was from the encoder, and we're using that to generate the key and the value. So the attention matrix ends up being created from a combination of values within the encoder and values in the decoder to generate the attention matrix. And then the values from the encoded input get multiplied by that attention matrix to create the output of cross attention. So we've kind of injected the embedding from the encoder into the decoder, and we've done that in a way that accounts for both the encoder and the decoder's values simultaneously. Hopefully that jives. So now that we've sort of injected the values of the encoded representation into the decoder, we then just kind of add it with a skip connection to whatever the previous values were. So we have this mangled relationship between the encoded input and whatever values exist within the decoder input, and we combine them together. Just like with the encoder, we just talked about one block, but you can actually stack these on top of each other. So you can get the encoded representation to cross-attend with the decoded representation throughout various layers of different blocks stacked on top of each other, all of which create a very meaning-rich abstract representation of a combination of the input to the decoder and the input of the encoder. And that's basically the entire transformer. At this point, it's just bookkeeping. So the end of all of these shenanigans is a big list of vectors. And what we kind of want as the output is words, right? We want to output a sequence of words that represent our predictions. The way we do that is we apply a dense network, just a linear network. And here it's called linear because there's no activation function. It doesn't really matter. But what we do is we take whatever our vectors are and we use a neural network to expand that vector such that there is a spot for every word in our vocabulary. Each of these vectors gets expanded into a vector that represents every word in the vocabulary. Then we apply softmax, just like we did within the transformer, that gives us basically big numbers and small numbers. And we say whichever the biggest number is the word that our model predicted. So for the first vector, the one that originally started with the start token, it might feed into a vector that then gets exploded into our a spot for every word in our vocabulary, then softmax, and then hopefully the value with the highest value would be the word je. And then the next vector would, get expanded to a spot for every element in our vocabulary, and then softmaxed, and then hopefully the largest value for that would be sui, so on and so forth. And as a result, we have predicted our output sequence essentially. So a natural question might be, what's the big deal? That's the transformer. We covered it. It's for English to French translation. How did this explode AI and allow for all of this crazy stuff? Well, you can kind of slice and dice and experiment with this architecture, and it turns out you can apply it to a ton of applications. I'll give you a few examples, but there's practically an innumerable quantity. One of the very famous examples is GPT, as in ChatGPT by OpenAI. GPT is the generative pre-trained transformer, and it's what's called a decoder-only style transformer. Basically, the idea was, instead of framing words as inputs and outputs, what if you basically got rid of the encoder entirely, and you took whatever input you had as just the beginning of your decoder input, and then use that to generate the output. So when you talk to ChatGPT, essentially what happens is whatever you said ends up as the input of the decoder, and then the model finishes whatever the sequence was by generating words until it thinks it should stop. And that's how it talks to you. There's also image generation models, like you might have heard of Midjourney. There's also video generation models like Sora. You might be like, whoa, how are you doing video and image generation with this thing that's designed for words? Well, it's not really designed for words. It just takes sequences of vectors and correlates them together. So for instance, if you think of a region of an image as you kind of unravel it into a vector, you break up an image into this sequence of vectors, and then instead of having your positional encoding be a sequence, you say what position in the image it was, and you add that information. You can create a transformer that can suddenly understand images and do all sorts of stuff. You can do object detection, you can do image generation, you can do video generation. The amount of things you can do with the transformer is absolutely absurd. And it's maybe sometimes a little scary, but it's also incredibly exciting that we as humans have unlocked this new tool about understanding things. And frankly, we don't really understand it completely. And there's a lot of research that's going into how can we manipulate this architecture? Is there anything we can do to bolster this architecture? Is this just the beginning? Are there other architectures that employ some similar strategies that might be even more robust and more applicable to more applications? I have no idea, but I'm very excited. You might have noticed that throughout this video, there were a variety of references. These are references that I wrote. I've been writing about AI for a little while now, and I'm trying to make this a bit of a thing. I'm really seriously trying to create higher quality educational content around artificial intelligence to make it more accessible to more people. If you're interested in that and you would like to support me in this venture, please consider subscribing to my writing. It's designed to be a complement to these videos, and it would mean a lot to me if you would check it out. Otherwise, I really appreciate comments, like, comment, subscribe, all that stuff. And thank you so much. My name is Daniel Warfield, and this was the Transformer, intuitively and exhaustively explained.